Hello, this is a short course on gas chromatography, interface with infrared spectroscopy and its applications. My name is John Schneider. I'm a analytical chemist retired from Argonne National Laboratory, currently teaching at chemistry at the College of DuPage. If you want to get some more information or have any questions, there's my email. So, why am I teaching this course? So I've been involved in developing analytical methods, particularly early on. I was involved with developing the GC-FTIR interface, been involved with using field analysis and working on site with a lot of mobile labs, currently teaching at the College of DuPage in Glen Ellen, Illinois. And I was part of a team at Argonne National Laboratory led by Jerry Reedy that invented GC matrix isolation FTIR, which won an R&D 100 award. And we published a lot of papers and gave a lot of talks. This technique allows the analytes separated by capillary gas chromatography to be trapped in an inert matrix of argon or nitrogen and analyzed by Fourier transform infrared spectroscopy. This technique produces high quality spectra of matrix isolated compounds that allows identification of specific isomers that cannot easily be done by GC mass spec. The sensitivity is superior to other GCIR methods. That's for the matrix isolation one. I have also used GCIR in my laboratory to solve analytical chemistry problems for several clients over the years. I have used a light pipe GCIR and, of course, the matrix isolation GCIR technique. Okay, so this course is an attempt to give you a background. If you're interested in potentially doing GCIR, we're going to start out by not assuming anything. We're going to talk a little bit about what is gas chromatography, give you an introduction to gas chromatography. It's not meant to be comprehensive, so just meant to give you a taste if you're not aware of it. If you want, you can find a lot more about GC. There's a lot of information out there about GC. Then we'll also talk a little bit about infrared spectroscopy. Again, just very, very briefly, a lot of information out there. Then we'll talk about, well, why would you want to combine GC and IR? Why would you want to do the interface and then use them both? And then we'll talk about the different kind of GC-IR experiments that you can do. There's a light pipe, cryogenic trapping, and matrix isolation. So we'll talk a little bit in depth about all three of those. And then we'll talk about applications. What would this be good for? And then we're also going to talk a little bit more specifically about applications to the cannabis industry, kind of a newer development here. And I think there's a lot of application for GCIR in that particular industry. Okay, so just real quick here, start out simply. Chromatography was invented by a guy named Mikhail Svet, 1901. He was a Russian botanist, and he was trying to clean up some plant material, took the Roundup plant material and tried to wash it through some sand with water. And in the process, he saw the separation of some of the pigments in the plant material and the separation of the chlorophylls, xanthophylls, and carotenoids, and saw the different colors and realized, well, there's something going on here with this. And he called this chromatography, from the Greek for chroma, color, and graphene for writing, so color writing. Svet named the new technique based on the fact that it separated the components of solution by color. So there's a lot of different kinds of chromatography. You're probably familiar with some. Paper chromatography is used a lot in middle school and high school laboratories, chemistry labs and things, where you put some ink or some kind of food coloring, make a spot on some paper, and then you use the paper as a wick and let some water or some kind of water solution run up through the paper, and you can see the separation of the components and the different colors as the water moves along the line. There, the water is the moving phase or the mobile phase. And we have thin layer chromatography, liquid chromatography, high pressure liquid chromatography, very, very popular for biological type compounds, ion chromatography, and then what we're going to talk a little more about here, gas chromatography. So in all chromatographic separations, the sample is transported in a mobile phase. So in gas chromatography, the mobile phase is a gas. Liquid chromatography, the mobile phase is a liquid. The mobile phase could be a gas, a liquid, or a supercritical fluid. A little more of a specialized technique. The mobile phase is then forced through a stationary phase, held in a column or on a solid surface. So in the paper chromatography, the paper is the stationary phase. The stationary phase needs to be something that does not react with the mobile phase or the sample. it can interact, it interacts with them, it certainly does, but it does not chemically react with them. The sample then has the opportunity to interact with the stationary phase as it moves past. Samples that interact greatly then appear to move slowly. Samples that interact weakly then appear to move more quickly. Because of this difference in rates, the samples can then be separated into their components. So if we look upon this as the analytes, and the little bluish ball in the middle there is the stationary phase, we're going to have an equilibrium going on between the analyte that's going to be in the mobile phase versus what's going to be either attracted to the surface of the stationary phase or actually dissolved in the stationary phase. Yeah. And so that ratio there is going to be called the distribution coefficient, and every different compound, every different chemical, every different analyte will have its own distribution coefficient depending upon what the stationary phase and what the mobile phase is. And the difference in those distribution coefficients is what's going to allow for the separation to occur here. So as we see this, as your analytes move through the stationary phase, and one simplistic way of thinking about this is if you're going on a hike with two different kinds of people, one kind being people that don't like apples, another being people that love apples. If you walk them through a apple orchard, then the people who don't like apples would just march right on through. They would not be affected by the apples in the apple orchard. They would go through the apple orchard first. The people that like the apples, have an affinity for apples, they'd be tempted and they would have to stop and maybe eat some apples along the way. So they'd be slowed down because they have an affinity for the apples, and they would come out as a second group. So what this would end up looking like, anytime you have a flowing system, you're going to get some diffusion. So not all the analytes are going to come through at the same exact moment. There's going to be some that's going to be by diffusion traveling a little faster, some a little slower. So the end result is you get this Gaussian distribution here, and it's called a peak. And this would be a real idealized, perfect, chromatographic peak. Nice bell-shaped curve there. That would be how one component would look coming through a column. And in the x-axis, we would have time, the time it takes to go through the column or through the stationary phase. The y-axis would be the number of analytes coming through, or the detection of analytes coming through the system. Okay, so if we have more than one component together with different distribution coefficients, then these things are going to be separated in time. And you see the red and the blue analytes here getting separated with time. The longer they're going through the system, the more separated they will get. They'll also get diffused more, so you get broader peaks. So what that's going to look like is this. This is a idealized chromatogram. The result of chromatography, you usually end up with something called a chromatogram. The peak there at the time 1, that's a nice sharp Gaussian distribution. Not total separation with the peak at 1.5. The 1.5 was on the column a little longer, so a little more diffusion, so it was broadened out. And you do not have what would be called baseline separation there, so it's not perfect separation. Then you got this other peak comes out much later at 2.5. There you do have baseline separation. But you see how that peak is even broadened out even more. That's because the more time it's spending on the column, the more the peak gets broadened out. There's things we can do to sharpen those up, using temperature programs in GC or using different solvent type programs in HPLC, but this kind of gives you the general idea of how chromatography works and what a chromatogram is. So for gas chromatography, this is going to be good for volatile samples. Things that are going to be able to be volatilized up to about 250 degrees, things that are going to break apart with heat, or things that are not very volatile are not necessarily good candidates for gas chromatography. Usually you're injecting 1/10 to 1 microliter of liquid, which is going to be vaporized to 1 to 10 mils of vapor. And you can detect usually less than 1 ppm with certain detectors. And as gas chromatography can kind of lend itself easily to automation for injection and data analysis. So in gas chromatography, we have to worry about sample preparation. Not everything is able to be just put right in a GC. Usually things are dissolved in some kind of solvent, usually an organic solvent, because most GC columns do not really like water. You've got a sample inlet, and usually it's an injection port, and you've got a septum that you have to use a syringe to put your inject your sample in through. You talk about packed versus capillary columns. There's all kinds of information out there on columns. Recently, we have mainly all capillary columns. Packed columns are more for separating things and what you want to retrieve your analytes. So more preparative scale type work. Analytical work's usually all done on the capillary level. Detection, different kinds of detectors, and how do you interface with a detector? These are all considerations with gas chromatography. Here's a schematic of how a basic GC looks. You got some source of the gas, usually a cylinder or carrier gas. Well, it doesn't necessarily have to be. It could be a compressor. But usually you're going to use inert gases, so it's probably going to be a cylinder. Flow, you control the flow coming in, you control the pressure coming in, you put this through an injection port, which is where you're going to introduce your sample. Again, we'll talk a little more about that in a second. After the injection port, you have a column. Lots of possibilities with the columns. That's where the separation is going to occur. And then as the samples and the gases leave the column, they go through a detector where they're counted or measured, and you get a result that you can record that results in a chromatogram, which is what we got in the little computer screen there on the right. Okay, so the carrier gas supply must be at a constant flow rate, so that retention times or retention volumes may be equated. It has to be very reproducible because if something comes out at 2 minutes, you want it to always come out at 2 minutes. That's the retention time is something you can use to help identify what you're looking for. The choice of the detectors will often dictate the gases that are used. Common gases, helium is the most common gas used, inert gas. Helium is getting a little bit of short supply. Nitrogen is also a very good gas for GC, not quite as good as helium. Hydrogen is actually a better gas, but hydrogen, people get kind of worried about it being flammable or explosive. Not really as much a concern as we think, but it's a concern, and argon is also a possibility here. Okay, in the injection ports are in GC are typically heated so that the sample is going to turn instantly into a vapor. Usually the sample is going to be dissolved in some kind of organic solvent. So you're not usually injecting the sample straight. It's usually a dilute solution. And in this injection, you inject with a syringe. You got a little picture of a syringe there, I think. And you're going through a septum. And there's many different modes you can use. There's a split mode because only a small amount goes onto the capillary column. You can only have about 1 ml a minute going on a capillary column. So you might split the injection, 10 mils going to the split vent, 1 mil going on the column, or maybe 100 to 1 or 1,000 to 1, depending on how much you want to go on the column. You can control that. If you want to get more on the column, there's something called the splitless mode, where you turn the split valve off for a period of time and then turn it on to blow the rest of the solvent out of the system. And then in some cases, kind of a little bit rare, you may not have any splitting going on at all. You just do directly on column, and you'd have to inject a very, very small volume of sample in that port. GC columns, unbelievable number of GC columns out there. They usually have an inside diameter of a millimeter or less. 0.32 millimeters, very, very common. The more narrow the bore, the better the analytical column, but the smaller the capacity will be. So if you're going to inject a lot of stuff, you have to have a wider bore column. And there's different kinds of stationary phases you can look at. There's different thicknesses of stationary phases. There's an unbelievable amount of GC columns out there. Fortunately, with capillary columns, most of these columns are going to be very, very efficient. So you may not need to worry about which kind of column you select unless you've got a very specific analysis that you're doing. And there's also packed columns, which you can find a lot of information out there about columns. The detectors, GC detectors, you have ideal detector characteristics. You'd like a detector that would detect everything, universal response. You'd like sensitivity. You need to have reproducibility. You like a large dynamic range, linear dynamic range, if you're going to do quantitative work. Some detectors are very, very sensitive, but they're not very reproducible, and they're not going to have a very large dynamic range. Ones that we use for quantitation, we really need to have reproducibility in the large dynamic range. For all of these, I think with capillary in particular, you want a fast response time. And non-destructive, that's maybe kind of my bias. If you want to do something else with your analytes after it goes through the detector, you want it to be non-destructive. Of course, GCMS and flame ionization we're going to see are very, very common detectors, and they're both destructive. Here's a list of detectors. Flame ionization, one of the more common ones. Thermal conductivity, electron capture, very, very sensitive and specific for chlorinated and nitro compounds, electron capturing compounds. Thermionic, very specific for nitrogen and phosphorus compounds. Atomic emission, infrared, which is what we're talking about here, and mass spectrometry. So flame ionization is kind of like just what it says. What you have coming out of the column ends up going through a flame and getting burned. You have a hydrogen and air supply to make a flame. As this goes through the flame, the analytes get ionized in the process of burning, and then those ions are detected. So that's what the flame ionization detector is. So anything that burns will be detectable by flame ionization detectors. So it's a fairly universal detector, and it's a very good reproducible detector, and it's got a very good linear range, and it's a very good detector to have. Thermal conductivity is much less sensitive. Here you have a column flow from the column, and you have a reference flow, and so you're comparing the thermal conductivity of these two flows to a wire. And when your analytes come through, it's going to change the thermal conductivity of your reference, of your sample gas versus your reference gas. That's what you're picking up. So not very sensitive, but this is good for detecting liquids, things like water. It's a very common detector in that it's good for students. It's kind of hard to destroy this detector, but it's not too useful for too many things except for some specialized situations. Electron capture, using a radioactive source with beta particles, and those beta particles, as your sample comes off the column, goes through this source, and then you have some of the analytes may capture some of the beta particles coming off of the electrons, and then those get ionized, and those are what makes the detection. So very, very sensitive, very, very good for nitro compounds and chlorinated compounds. Very good sensitivity, pretty good linear range, and you can see very down to very, very low levels with this. Nitrogen phosphorus detector, just as it says, a heated bead that when you run your analyte stream over this, nitrogen and phosphorus compounds are going to be specifically detected as they are getting ionized. There's a lot of unknown what goes on with exactly how some of these nitrogen phosphorus detectors work. Atomic emission. This is a kind of a specialized detector that was out a while back. What would come off the column would go into a microwave cavity where you have a plasma. Then the plasma would give off light, and then the light would be looked at, and the different elements could be detected. So this was good for detecting specific elements and certain packages of elements that would come off. Kind of a nice thing. We did a little work with this. Unfortunately, not always as reproducible as you would like, but if you have a specific task, this could be a very good detector. GCMS, very common, one of the most common detectors. What comes off the end of the column goes through an ion source, gets ionized, and then goes through a mass filter, and then you detect those ions. For the most part, what you're doing when you put it through the ion source, you're ripping apart the molecule, and then you're looking at the pieces that go through the mass filter. So you got to remember with GC mass spec that you're not looking at your compound directly, you're looking at the fragmentation pattern. And depending on how your mass spectrometer is tuned, that's going to determine what your mass spectra look like. So mass spectra are not absolute. Mass spectra depend upon your particular mass spectrometer, how it's going to look. And that's why everyone tries to tune according to certain conditions so that we all get mass spectra that agree. So it's kind of artificial in a way. Different GCIR interface. Capillary columns have an effluent of 0.5 to 2 mils per minute. Packed columns much more, up to 30 mils a minute. Most detectors are at ambient pressure and can take all of the GC flow. Some detectors aren't. Mass spec has under a vacuum, so it can't handle all that flow. So a lot of times you have to split some of the flow off so that you're not getting all what comes off the end of the column that goes into the mass spectrometer. In infrared, you've got one detector that is at ambient, the light pipe, And the other two, the cryogenic trapping and matrix isolation, are also under vacuum, just like a mass spec. So when you're trying to package these things together, you got to take these interfaces into account. Okay. And we just kind of mentioned this a little bit. Some have a direct flow into the detector, some you have to split to lessen the flow. In other cases, you might have to increase the flow with an open split, add gas to it. Okay, there's a little bit about GC. Now to talk about infrared briefly. Infrared spectroscopy is an analytical technique which helps determine structure. It destroys little or no sample. The amount of light absorbed by the sample is measured as wavelength is varied. The infrared spectroscopy measures the bond, vibration frequencies in a molecule and is used to determine the functional groups. So here's what we're talking about here in terms of the infrared light. It's in the wavelength of 10 to the minus 3 centimeters. It's in the region where you're seeing molecular vibration. So this is for molecular type analysis. You can look at molecules with infrared light. Okay. The infrared region is just below red in the visible region. Wavelengths are usually 2.5 to 25 millimeters, although chemists most commonly use wave numbers or reciprocal centimeters instead of the wavelengths. Wave numbers are proportional to frequency and energy. So you have that consideration. So if you're talking about infrared, a lot of times you may be talking about wavelength or wave numbers. You have to be aware of that. And we're talking about molecular vibrations here. Covalent bonds vibrate at only certain allowable frequencies. That's according to quantum mechanics. And there's certain particular frequencies will correspond to absorptions if you're doing absorption infrared, or if you're heating up the molecule, it could be giving off that light, transmission. Here's some little schematics to show you how on the left there we're showing electronic transitions, while on the right you got the same kind of transitions going on, quantized depending upon what kind of vibrations are going on. And there's some nice little cartoons below to show you some of the basic vibrations, bendings, and stretching that go on. So here's some of the stretching frequencies. You've got the reciprocal centimeters there, so the CH1 is around 3,000. Depending upon what is attached to the carbon, got deuterium or carbon, it's going to determine where the stretching frequencies occur. And you've got single, double, and triple bonds, and that's also going to have an effect. So frequency decreases with increasing atomic weight. Frequency also increases with increasing bond energy. Vibration modes, nonlinear molecule with N atoms usually has 3N minus 6 fundamental vibration modes. So you've got, even a simple molecule like water, you've got all kinds of vibrations that are going on, all kinds of absorptions that are going on. So this kind of seems to make it a little complex, but whole molecule vibrations and bending vibrations are also quantized. So no two molecules will give exactly the same infrared spectrum, except in nanometers. So that's kind of powerful. If you want positive identification, if you get the infrared spectrum and it matches, you know is what you got. You have not artificially tuned the infrared that you get something you just don't do, you know. Simple stretching, you got this region here where you got the simple stretching going on, 1,600 to 3,500 reciprocal centimeters. And then we got this complex region called the fingerprint region, which is very, very powerful for identification, from 600 to 1,400 reciprocal centimeters. Some materials are infrared active and some are inactive. A polar bond is usually infrared active. Non-polar bond is a symmetrical molecule, absorbed weakly or not at all. Kind of all the stuff kind of cancels out. So carbon dioxide does not absorb very well. Carbon tetrachloride does not absorb very well. Bent molecules and most everything else, you know, will absorb pretty good. And the more polar the bond is, the better the absorption is. Carbonyls are really good infrared absorbers. You know. Here's kind of a summary of where these absorptions take place. And if you have absorptions in these regions, a lot of times you can identify what the functional groups are. So the strengths and limitations, and usually infrared alone cannot determine a structure, unless in some cases you have a really good spectrum and you can get a really nice positive identification. Some signals may be ambiguous. There's so much going on. There's a lot of information there. We just don't, you know, have it all figured out at this point. Functional groups usually indicated. If it's got a carbonyl or hydroxyl group, you can normally determine that. The absence of a signal is definite proof that the functional group is absent. So if there is no carbonyl, there's no carbonyl in the molecule. Correspondence with a known infrared spectrum confirms the identity of the compound. So these things leave very specific spectra that if you get a direct positive hit, you got a pretty good thing there. Okay, different kind of spectrometers. The dispersive, 30 or 40 years ago, this was very common. You had a reference beam and a sample beam. You had a chopper, a monochromometer, and you would scan through this thing and take the infrared spectrum very, very slowly. The more slowly you did it, the better the spectrum you got. Very nice, but this would not lend itself at all to GC, where your sample comes through in a matter of seconds. So fortunately, the FTIR spectrometer, which uses an interferometer, has better sensitivity, less energy is needed from the source, completes a scan in 1 to 2 seconds, and takes several scans and averages them. Has a laser beam that helps keep the instrument accurately calibrated. So I'm not going to go into how Fourier transform infrared spectrometer works. There's a whole bunch of other information available on that. You may want to look into that. And the crux is it's fast enough for real-time GC detection. Applications for infrared. Identification of inorganic and organic compounds, identifications of components of an unknown mixture, analysis of solids, liquids, and gases, remote sensing. A lot of the infrared work that's from outer space or detecting what gases there are out in space or in any distance, that's remote sensing. It's very powerful for infrared. The measurement and analysis of atmospheric spectra, solar radiance at any point on Earth, long-wave terrestrial radiation spectra, and can also be used on satellites to probe space. Something to keep in mind is that different physical states will have an effect on the infrared spectrum. The liquid phase, and you have a lot of molecular interactions which broaden the absorption peaks. We're going to see more of that later. Solid phase, even more so. Molecular interactions broaden absorption peaks. So you get nicer looking spectra with the gas phase, which lack molecular interaction and sharpen the absorption peaks, and also matrix isolation, which look a lot more like the gas phase spectra. Okay, again, that was real quick about IR, a little background on GC, a little background on IR. You probably know one better than the other. If you're a little weak, you might want to look elsewhere for more information about either one. So why would we want to combine these? Why would we want to do this GCIR experiment? Well, if we combine the separation ability of GC and the structural information from infrared spectroscopy, this is going to give us a lot of information that's going to give us information that's going to be complementary to what we get by GC mass spec. Functional group detection, which can be very, very powerful, and isomer specificity, which is very important when it comes to a lot of the analysis we want to do. We're doing things that any kind of a bioactive molecule, it's going to be very important to know that we got the isomer we think we do. This comes to the food industry, the flavor industry, medicine, lots of applications. Isomer specificity is very important. And mass spec does not do it as well as IR does, and certainly the best is to have both of them together. So GCMS versus GCIR, gas chromatography with mass spectrometry detection is a state-of-the-art method for the identification of unknown compounds. Can't deny that. GCMS, however, is not infallible, and many compounds are difficult to identify with 100% certainty. The problem with GCMS is that it's a destructive method that tears apart a molecule. So you're not looking at the whole molecule, you're looking at the pieces of the molecule. In infrared spectrometry, molecular identification is based upon the infrared absorption of the whole molecule. This technique allows differentiation among isomers and yields information about functional groups and the position of such group in a molecule. So GCIR complements the information obtained by GCMS. To kind of give a simplistic analogy of what we're talking about here, if we're looking at parts of a human being, GCMS could tell you, oh, this is a hand. GCIR could tell you if it's a left hand or a right hand. Okay, different kinds of GCIR interfaces. Real-time GCIR can be done using a flow cell or a light pipe. The infrared spectrum is obtained in real time as the sample elutes from the end of the GC column. And there's also trapping GCIR, which is done by collecting or trapping the analyte after GC separation. Trapping is normally done cryogenically, and the sample analyte infrared spectrum is obtained on a liquid, solid, or in the matrix isolated form. Trapping GCIR can be done cryogenically, collecting effluent from the GC Has a solid on a surface. This is cryogenic trapping, and it's commercially available. There was a company named Bourne Scientifics, headed by Sid Bourne, who was involved in developing this technique from the beginning. The infrared spectrum is obtained from the solid analyte. This method is sensitive but produces low quality spectra because of absorption from the molecular interactions. It doesn't have sharp absorptions found in gas phase or matrix isolated IR spectra. GCMIR, this was invented at Argonne National Laboratory. The guy who was lead on this was a fellow named Jerry Reedy. You know, in this technique, the effluent from a GC is frozen from a continuous strip in an argon matrix at liquid helium temperatures around 10 degrees Kelvin. Matrix isolation, FTIR, has sensitivity comparable to mass spec and produces spectra with sharp absorptions because of the lack of the band broadening caused by molecular interactions or rotation. This instrument can be used to confirm identifications made using GCMS analysis and provides highly reliable identification of suspect and unknown compounds. Okay, so here's the three techniques, three different interfaces. The light pipe, the analyte is in the gas phase as it travels through an IR cell or light pipe. Cryogenically, the analyte is trapped on a surface cryogenically, so it's going to be a solid phase. Matrix isolation, the analyte is trapped in a matrix of inert material. Usually it's going to be argon. Here's some pictures of the three different systems. The light pipe is the most common, the one on top there. Agilent or Hewlett Packard used to make a GCIRD system. Cryogenic trapping, we got one on the lower left there. And matrix isolation, this is a GC matrix isolation FTIR system that's in my laboratory. This gives you an idea of the kind of spectra that you get from these different techniques. These are all 2,6-dimethylphenol. The one on the top is a solid phase spectrum. You can see on the left side of the spectrum there, the very broadened out OH absorption. That's because of the intermolecular associations between the particles. Down below, in the middle, we have the gas phase spectrum of the same thing. There you see the OH peak is much more sharpened up. And then down the bottom, we have the matrix isolated version of the same thing. Again, the peak is very much sharpened up. So this kind of shows you the kind of spectra you get. Computer searches tend to like the sharper peaks. So the gas phase spectra lends itself very much to computerized searches of libraries, and so does the matrix isolated ones. Solid phase, you can do it also, but it's not going to be quite as clear for the analysis. What is a light pipe? The light pipe is a vapor phase spectra is going to be what you're going to be getting. It's going to have relatively low sensitivity because what comes off the end of the gas chromatograph goes through the light pipe very, very quickly, and there's not much sample there. The infrared spectrum is, however, obtained in real time. This is a schematic of a light pipe for the GCIR. See, the sample comes in one end, travels through the column, comes out the other end, and we have a KBR windows or some kind of a salt plate windows that allow the infrared light to go through the same tube. The tube is gold coated, so it gives the better transmission of the infrared light. So the sample is only going to exist in this tube for a very short time, only enough time for you to maybe collect 2 or 3 spectra at the most. So that's kind of both an advantage and a disadvantage of the light pipe. So infrared absorption with the light pipe, an infrared detector from gas chromatography. The IRD flow cells is optimized for capillary GC peaks. Sample preparation identical to GCMS. Uniquely complements MS spectra with FTIR spectra. Multi-vapor phase libraries are available, so there is a lot of information available out there with the libraries. Combines the separating power of GC with the structural identification of the FTIR. IR light from the interferometer enters the flow cell assembly and passes through an optical window into the light pipe. The light pipe is a glass tube 120 millimeters long with an internal diameter of 1 millimeter. The volume in the light pipe is usually around 1/10 of a mil. So you see it's not going to have much volume in there. The inside of the tube is plated with gold to prevent the light loss. Material eluting from the GC flows through the light pipe and absorbs part of the infrared light. The remaining light exits through the light pipe through another optical window. So these are typical spectra you can get using the light pipe. See the very, very nice spectrum. So you can do a very good job of differentiating between isomers using this, and this kind of lends itself very, very well to the computer searching. You can also do functional group analysis where you have the total infrared chromatogram on the left here, and then you're able to pull out different regions. 3600 region where the alcohols occurs on the upper right there, and then you have the carbonyl region or the aromatics. So by looking at those chromatograms, you can determine if a peak has the alcohol or the carbonyl functional group in them. That can be very, very powerful for different kinds of analysis. You do a good job of GCIR isomer identification with this, particularly looking down at the fingerprint region. Different ways of setting up the an experiment. You could have the effluent from a GC going through a infrared flow cell and then into a MSD. That's why it's nice to have the infrared as a non-destructive technique, because what comes out can go into the mass spec. You could have a splitter and send some over to the light pipe and some to the mass spec. In this case, you'd probably want to have more going to the infrared, because the infrared is about 10 to 100 times less sensitive than the mass spec. Or you could have the injection port going to 2 columns, and then those both going to different detectors. Cryogenic trapping. In cryogenic trapping, you're going to get solid phase spectra. You're going to also have high sensitivity, but lower resolution looking spectra. Your resolution is a function of the FTIR you use, but the spectra themselves, the peaks will be broadened out. And here you're going to be obtaining the infrared spectrum after the GC part. It's not going to be real time. Discover IR is one company that makes this. They do a micro deposition on a cryogenically cooled infrared transparent disk, solid phase transmission FTIR spectra with high resolution. And there's 4,000 FTIR spectra of drugs included in the library that can come with this. Again, the searching is not going to be as good as it would be with the vapor phase. And run standalone or in parallel with the GCMS. And here's kind of a schematic for the cryogenic trapping. You've got this zinc selenide disk, and you're going to be collecting a trail of the solid material frozen on the surface of that. You can collect several tracks on this. After a while, these disks should be reused. You can wash off the solvent, or they may just sublime off. So this is all going to be done in a vacuum. So the collection disk is infrared transparent. A beam of infrared energy from an interferometer passes through the disk along the deposition track, and the infrared spectra are collected at 0.3 second intervals. The width of the deposition track and the infrared beam focus point are matched at approximately 100 microns. As a result, one can obtain good quality spectra on nanogram amounts of analytes, so it can be very, very sensitive. The infrared spectra are solid phase spectra, which are not very good spectra, but sensitivity then obtained by light pipe instruments. They're trying to compare it to light pipe. Spiral deposition tract of the collection disk has capacity to accommodate several hundred samples to be analyzed over a runtime as long as 2 days. Keep it in there too long, and then you're probably going to get some contaminants starting to come out, freeze out on the surface. And here's what I'm talking about. Here's some of the infrared spectra that you get using this technique. Usable, but not as satisfying as you get with the vapor phase, or you'll see with the matrix isolated. Okay, now going on to matrix isolation. Matrix isolation, you do cryogenic trapping also in a matrix of argon. Got high sensitivity. It gives you high quality spectra. And again, just like cryogenic trapping, it is cryogenic trapping. The infrared spectrum are obtained after the collection phase. So here's a paper we published in Analytical Chemistry showing this technique when we first came out with it. This picture on the right is a gold-plated carousel which was moving, rotating with time. The GC track is being laid down. That's a track of the argon. We add about 2 to 3% argon to the carrier gas. You put the effluent from the GC column very, very close to the surface, the helium gas gets pumped away, and we end up having this nice track of helium being laid down, which comes off kind of like it's a very nice amorphous blob, kind of like liquid cement being laid down. And this is kind of the way it looks. Your analytes are trapped in an inert matrix of solid argon at 10 degrees Kelvin. So you have low temperatures, you have minimal rotation line broadening, and you have the samples are trapped in the matrix, so you have minimal intermolecular interactions going on. And in this case, we're seeing the yellow on the bottom is the gold surface. The blue balls are meant to represent the argon matrix. Then you have the analytes trapped in the matrix. Here's a nice little cartoon showing schematic how this would work. As the carousel is rotating, you have the end of the column positioned very, very close to the surface. Then the blue balls are the argon matrix being laid out. And those colored balls are wherever the analyte's coming out trapped in the matrix. So as analytes elute from the column, they and the argon present in the carrier gas, approximately 2%, co-condense on the optical cylinder. Helium, again, is going to get pumped away. It's a little too volatile. The cylinder is continuously rotated, creating a continuous elliptical matrix with trained elements. The cylinder is positioned and can be repositioned such that the infrared beam can be precisely focused onto any point in the matrix. The result is very high quality spectra with sub-nanogram sensitivity. There's a schematic of the cartoon a little bit closer up for you to see. Okay, here's a couple pictures of this system. This was the first commercialized by Matson Instruments and later on by Reedy Scientific, originally called a cryolect for a cryolytic collection system. And we have ours also interfaced with a mass spec. There's a picture of ours in our lab. Here's the gold plated carousel, and there's the vacuum chamber. We had a little glass plate over so you see it. And the effluent from the GC is coming in from the left there. And there's mirrors that focus the infrared beam on that too. It's a two-step process. Down below, we have a closed cycle helium refrigerator to cool down the discs. And we have the FTIR spectrometer on the right there. So these are the kind of spectra that we get compared with the vapor phase on top and the matrix isolated on the bottom. Again, the kind of spectra that really lend themselves very, very good to computer searches. Another spectrum there. This is the fingerprint region. Closer from when we first developed this. So GC matriculation FTIR was invented at Argonne National Laboratory in the mid-1980s. It can be used to confirm identification made using GCMS analysis and provides highly reliable identification of suspect and unknown compounds. So light pipe or cryogenic trapping interfaces are currently available. Libraries, vapor phase IR spectra are also available. Not as many complete units being sold. The matrix isolation unit was commercialized and sold. There are units out there. I don't know if there's anybody currently making one that you can order one from. The total infrared absorbance versus time and analogous to a total ion chromatogram. You can do some of the same kind of things you can do with mass spec. You can also do with IR. You can select infrared regions to look for specific functionalities, such as carbonyl versus time analogous to selected or extracted ion chromatography chromatograms. Here's kind of some of the companies that the light pipe has been available from. I think Pike and Bruker still have interfaces available. Cryogenic trapping, again, was Born Scientific, was from Sid Born. And then matrix isolation, Jerry Reedy, the inventor, and he had his company for a while. Okay, let's talk a little bit about some of the applications of the GCIR. Very, very good at isomer identification, functional group, and confirmation of results with GCMS. So this is not going to be a routine technique. This is going to be a little more sophisticated technique, which is going to be very, very powerful in certain applications. Here's kind of another comparison of the three different GCIR interfaces. The IR spectra type you get, gas phase versus solid phase versus matrix isolated, spectral quality, sensitivity, and cost. Light pipe's the cheapest, but also has the lowest sensitivity, and the others two are fairly expensive, but they also have high sensitivity. So the kind of tracings you get. On top you have an FID tracing, and then this is all the same run. The second in the middle there is a phase-sensitive infrared reconstruction. That's like an infrared chromatogram. These are all chromatograms. And then the one on the bottom shows the total ion chromatogram. So, these things can be set up so it's all going to, you know, colute and make sense. This is one run in this case. Applications for IR, GCIR, organics and water, aromatics and gasoline, oxygenates and gasoline, for environmental hazardous waste, i.e. soil contamination. In some cases, there were environmental pollutants that were very much dependent upon specific isomers. For dioxins, for example, certain isomers are much more toxic than others, so GCIR can be used to positively identify those. Drugs and forensics can be very, very important. Pharmaceuticals, to make sure you're working with the specific isomer you want to work with. Foods and flavors. A lot of these food and flavor companies, there's a lot of people out there that actually are doing all this. A lot of times this is not published that much. A lot of it's kept kind of secret. So GCMS is a little bit more known. GCIR is kind of the secret technique that people use. Homeland Security, used a lot for, not for identifying chemical agents directly, but maybe for identifying some of the signature compounds associated with them, and for explosives. People identify, who made this or who released this. Did some work with looking at air chlors to give an example of how this can be useful for identifying isomers. The PCB air chlors are chlorinated biphenyls, and air chlor 1221 is air chlor that's been chlorinated to 21% free radical chlorination. Before we looked at this with GCIR, it was not known there was any 3-chlorobiphenyl. The 2 and the 4-chloro are the favored positions. Using the matrix isolation IR, looking at this, we were able to pull out that there's also some 3-chlorobiphenyl that was co-eluting with the 4-chlorobiphenyl there. Here you see some of the spectra that we get with this. You can see that the biphenyl matches up with the one peak there at 5.48 minutes, and we have a 4-chlorobiphenyl. You see how the kind of spectra you get here when you have a hit. It's almost like unbelievable. It's almost like embarrassingly right on. And so, if you have a positive identification, it's a positive identification. So in this case, looking at the 3-chlorobiphenyl, we were able to look at the fingerprint region, and we were able to pull out the fact that the 3-chlorobiphenyl was there, was not previously identified. So we were able to show that there was some 3-chlorobiphenyl present in there. Kind of just show the power of the ability of the GCMIR to identify specific isomers. Mass spec, this was not something that was easily done. Mass spec had been used previously, and it was missed because the 3-chlorobiphenyl was co-eluting with 4-chlorobiphenyl, and the mass spectra are identical. So some other specific isomers here for some of these things. Also look at dimethylnaphthalines, anything where you have a lot of particular isomers possible. We're able to identify all the different dichloral, the C2 naphthalines in a mixture. Some other work here done for looking at particular isomers by GCMS. So GCMS versus GCIR, gas chromatography, the mass spectrometry detection is the state of the art for the identification of unknown compounds and forensic analysis. Absolutely true. GCMS is not totally infallible and is identified to identify many compounds with 100% certainty. The problem that GCMS is a destructive method that tears apart a molecule, whereas infrared, on the other hand, is based upon the infrared absorptions of the whole molecule. This technique allows differentiation among isomers and yields information about functional groups and the position of such groups in a molecule. So GCIR is very useful when it complements the information obtained by GCMS. Applications to cannabis. Well, In cannabis, you have exactly what we're talking about here. You have a lot of different complex flavor components, terpenes, cannabinoids, esters. These are all fairly large biomolecules where specific isomer identification is very, very important. So for the flavor components, GCIR would lend itself well to the quality control, being able to understand, is this particular uh, cannabis sample containing what we think it contains, and making sure that that corresponds with what we want to have in there. And on the other hand, it's also going to be true for the medicinal components, specific isomers for the THC and the CBD, and you can identify compounds of new interest. And the GCIR gives you another dimension, another thing to look at, another thing to confirm confirmation of the results you get by GCMS, or things you might miss by just using GCMS. And there's also already some people doing some work with this using the combination of GCMS and GCIR. We're looking at some of these kind of compounds. A lot of stuff out there in the literature, cannabis and forensics. Here's a specific one right here showing the differentiation between the infrared. The mass spec comes out to be the same. So analytical chemists must keep up with the need for analytical methods for this new growing industry. Talking about cannabis again here. GCIR has the potential to help solve many of the needs to understand how the components of cannabis affect the medicinal and recreational uses and assure the quality of cannabis products.